Our next lesson is called The Power of Exponential Growth. So you'll be starting by completing an opening exercise. It says 2 equipment rental companies have different penalty policies for returning a piece of equipment late. Company 1, on day 1, the penalty is $5. So you would start filling in your chart here, like so. It says on day 2, the penalty is $10. On day 3, the penalty is $15. Remember, these are all dollars. I'll just put $sign on the first one just to remind you of that. On day 4, the penalty is $20, and so on. Increasing by $5 each day, the equipment is late. Company 2, on day 1, the penalty is 0.01. On day 2, the penalty is 0.02, or 0.01 and 0.02. On day 3, it's 0.04. On day 4, the penalty is 0.08, and so on, doubling the amount each additional day it's late. So what I'd like you to do is now pause the video. You are going to complete the 2 tables, as well as answer questions 1 on the bottom of this page, and also questions 2 through 4 on the next page. Once you finish question 4, you have completed the opening exercise, and you can resume the video to go over the answers with me. So right now, pause the video and complete the activity. Resume the video when you are ready to check your answers. Okay, so you've completed the opening exercise. Let's go over the answers together. With the 2 companies, day 1 is on the left, day 2 is on the right. I'm going to add right now to my table key the formula for each one, which I also address later in the questions. But this one on the left is having a change of $5 each day. So you're looking at f of t equals 5 times t. Your y-intercept, if we were to work backwards, would be 0. On the other side, since it's a multiplying pattern, you want to think about how we set up something like a geometric sequence. Here you would have f of t equals your first term times your common ratio, and then compensate for starting with the first term by using a -1 in the exponent. So using the 2 values in the table, check your tables quickly, make sure you have the correct numbers. Everything should have been adding 5 on the left-hand side. Everything should have been doubling on the right-hand side. If at any point during this you need to pause, just make sure you pause to get everything down. So now when I answer question 1, Jim rented a digger from company 2 because they thought it had a better late return policy. The job he was doing with the digger took longer than he expected, but it did not concern him because the late penalty seemed so reasonable. When he returned the digger 15 days late, he was shocked by the penalty. What did he pay, and what would we have paid if we had used company 1 instead? So 15 days late, he definitely ended up paying then $163.84. What would he have paid instead at company 1? So at company 1, he would have paid only $75. So it seemed like a good idea, but then he ended up doing 15 days late, which changed everything. Now looking at company 2, or question 2, which company had a greater 15-day late charge? We saw company 2 did. In number 3, describe how the amount of late charge changes from any given day to the next successes in both companies 1 and 2. So for company 1, each day you add $5. So whatever I have here, you need to make sure is on your paper. You may not have written it in the same way, but make sure you have the same information as I do here. We add $5 each day, which means it would be an arithmetic sequence. And then this is the formula that I also wrote on the front. For company 2, for each day, we multiply the previous day by 2. This would be more geometric because here we're multiplying, okay? So here we're geometric, and we have our formula here that I also wrote on the previous page. So special note over here on the side that I would like you to add, it grows at a faster rate in company 2 because of this multiplying pattern as opposed to company 1 where we're adding the same amount every single day. Then in question 4, how would the late charge have been after 20 days under company 2? So that's why it was important to actually write the formula for these, because if I write the formula, this is an easy question where I just replace the T with 20 and I find out it would be $5,242.88. So now let's take a look at the example together. It says, let us understand the difference between f of n equals 2n and f of n equals 2 to the n. So we just had a situation where one company was more of an arithmetic or linear situation, and the other one was multiplying, so we had a geometric situation. So we want to take a look at a different set of two functions that have a similar setup and really compare the difference between the two. So in A, it says complete the table of values and then graph the points n, f of n on a coordinate plane for each of the formulas. We're going to want to use our graphing calculator here to help us out with especially the f of n to the 2n, just to make sure we feel confident in our responses. Plus, I want to remind you how to actually go ahead and type in these values. Now, this first one we'll do by hand because it's very easy to just kind of plug the number in. You're just taking the number and timesing it by 2n. So 2 times negative 2 would be negative 4. 2 times negative 1, negative 2. 2 times 0 is 0. 2 times 1 is 2. 2 times 2 is 4. And 2 times 3 is 6. So we end up with our values that we can now go over on the other side and graph on the graph paper that you see. So negative 2, negative 4, negative 1, negative 2, 0, 0, 1, 2, 2, 4, and 3, 6. So you can tell before I even connect these that we're talking about a function that is linear. Now, they didn't say it was a sequence, so we are going to actually connect these to create a line. Then also, as usual, we should make sure that we label it. So we have f of n equals 2n. So there's my first function. Now, why did it turn out linear? Well, if we take a look, this was adding 2 every single time that simultaneously we were adding 1 on the other side. So we think about rate of change and slope that we've learned about in the past, that ratio stays 2 over 1 as a constant rate of change the entire time. Now let's look at f of n equals 2 to the n. And I want to go to your graphing calculator to do this. Now looking at our graphing calculator, let's practice quickly. You're going to go to your y equals screen, and we're going to type in 2 to the n by hitting 2. Then we're going to raise it to the power of n. So remember, you're going to use your caret button to get it in the exponent position, and then you're going to type your variable key, which is next to alpha. When we go to graph this, we would hit zoom 6 for the standard window, and you get an idea of what this looks like. As always, though, I say to you, it's hard to find the exact value, so you want to look at your table by going second graph, and we will use values from this table to enter into ours. Now, you see there's a lot of decimal values coming up here. I'm going to remind you of how we can make those fractions. You can take that number on the home screen and convert it to a fraction by using the alpha y equals screen. It will do those conversions for you. I will remind you by reminding you what happens with exponent rules. So on our table, we will fill in our values. We could tell from the table that 2 to the 0 was 1, 2 to the first is 2, 2 squared is 4, 2 to the third power is 8. These are some of your exponent rules. 2 to the 0 power is 1. We investigated that in the year previous. For our negative exponents, remember what we're supposed to do with those. If I have 2 to the negative 1, I write it as a fraction, and the negative exponent is telling me to take it and flip it and then make my exponent positive. So it said 0.5 when you actually looked at the table, which you could write down, but that's also the same as 1/2. When I did 2 to the negative 2, it would be 1/4, because we would have 2 to the negative 2, we would write it as a fraction and flip it, and 2 squared is 4. So now we're going to create this graph. Negative 2 1/4 would be about there. Negative 1 1/2, 0 1, 1 2, 2 4, and then 3/8, which you can see is above our other function. Now, if we go back and look at the graphing calculator, there is a picture of my graph, and you can see it gets all the way down to the x-axis and never goes below it. So when I go to connect these, I want to continue up in this pattern, and I want to follow this curve, and we're going to draw it really close to the x-axis like that to show that the pattern continues, but that it's never going to drop below that y-axis. This has a very special name. So we're going to circle this, and we're going to draw an arrow so that we can explain what this is. This is called an asymptote. Yes, a very weird word. And what this means is it will never go below y equals 0, or in other words, the x-axis. Sorry if I was saying the y-axis. It should be the x-axis or y equals 0. And then lastly, we want to go back and label our function. This is f of n equals 2 to the n. Okay, so now we want to describe the change in each sequence when n increases by 1 unit for each sequence. We already started to look at this in the first one. We had f of n equals 2n. For every increase in n by 1, f of n increases by 2. Now, on the other hand, if we have f of n to the 2 to the n, here for every increase in n by 1, let's take a look up here. We don't have that constant adding. Now we're multiplying. Every single time we move down the table here, we are multiplying by 2. So we will say f of n increases by a factor of 2 because we are doing the multiplying pattern. And our last example, example 2, a rare coin valued at $500 appreciates. Now, appreciates means it gains value, okay, at a rate of 5.2% a year. Show the formula that will model the value of the coin after t years. So if this is a percentage, that means we're looking at more of a geometric type situation. So we want to use a function of time. Our initial value, our principal amount is 500. So keep in mind, that's not our first term. That's what's across from 0. It's our initial value, not our first term. Our rate, remember, it needs to be changed to a decimal. So 5.2% means you need to back that decimal up 2 spots, and we want to do 1 plus the rate. So 1 plus 0.052. And then we're going to raise it just to the t. And again, not t minus 1 because we're not using the first term. We're using what's across from 0 or the initial value. So that would be a formula that would represent the situation. And that concludes your lesson on the power of exponential growth.